verification of completeness relation. We are now going to verify the completeness relation. We know the completeness relation is this. Let us consider the set of basis vectors. And we know the basis vectors are this. Okay, now if we consider the left hand side of the completeness relation, and now substituting these expressions for the basis vectors. And we know the bra E1 is the dagger of ket E1, which is a raw matrix. And we can now multiply the matrices. You see the left matrix has one column and the right matrix has one row, so we can multiply the matrices. Okay, all these are n by n matrices, and now if we add them, which is nothing but the identity matrix, or sometimes we call a unit matrix, and this is the right hand side of the completeness relation. You see, we started this relation. This is the completeness relation, so we started from the left hand side, and which we have shown that which is equal to the right hand side. Okay, next we consider matrix representation of the equation bra b is equal to a cat a. You see where a is an operator. Usually in quantum mechanics we consider linear Hermitian operator. Now to represent this equation, this is sometimes we call it transformation equation. You see when the operator acts on the cat A gives you another cat B, and in quantum mechanics matrices, the operators are nothing but matrices, and the vectors cat A, cat B, these are also matrices, but these are column matrices. Now we consider this set of basis vectors cat E alpha, and in terms of this, where capital N is the dimension of the space, we want to expand cat A and cat B, these two vectors, in terms of our basis vectors. Okay, so the this if we substitute these expansions cat A and cat B here, then we have this. So instead of summation over alpha, you see, instead of summation over alpha, we have used summation over beta for cat B and summation over gamma in cat A. There is no difference between taking summation over alpha, taking summation over beta, or taking summation over gamma, because all alpha, beta, gamma, all these indices, they run from 1 to capital N. Just to avoid complication, we have taken these sums like this. Now what you do, we want to take the inner product of this equation with get E alpha, and taking dagger of this we get bra E alpha. So we have taking the summation outside the bra, and this b beta is a complex number, so we can bring this one also outside the bra. And this inner product of two basis vectors, this is delta alpha beta, this is the Kronecker delta, and its value is 1 when alpha equal to beta, and this is 0 when alpha is not equal to beta. And this quantity is actually the matrix element of the operator capital A. As I said before, operators are represented by matrices, and so this matrix element, and we denote it by this. This is matrix element. Now we use the orthonormality property of the basis vectors. Actually this delta alpha beta is, this is equal to 1 when alpha is equal to beta, and this is equal to 0 when alpha is not equal to beta. So if we apply this, then we have this one can also be written as okay, this is a set of linear equations. Gamma runs from 1 to capital N, so this equation can be written as Okay, now substituting alpha equal to 1, 2, 3 up to capital N. So we get n number of linear equations. First one will be B1, alpha equal to 1 here. Alpha equal to 1, so the next one is alpha equal to 2. So will have B2 equal to 1A1. Alpha equal to 3, so we'll have B3. Okay, if we continue doing this, and the last one will be N equal to N1 A1 plus N2 A2 N3 A3 and An. Okay, so this set of linear equations now we can put into a compact form. we can write down this as B. This equation or this equation, where any one of these is known as the matrix representation of either of the above equations. Known as the matrix representation. Of the equation cat B equal to capital A cat A. That's all for now. In the next section, we shall study the unitary transformation, change of basis, and representation of operators in different coordinate systems.